So 2 to the power, and then the exponent here is this entire thing, negative 1 over x minus 2 squared. Okay, so first off, can I plug 2 into this function? Why not? Well, yeah, that's what it means if I can't plug 2 in. Okay, but what is about 2 that's a problem with this particular function? How do I know it's undefined at 2? Yeah. Yeah, if I plug 2 in and I look at the exponent part, there's a fraction, and that fraction's denominator is 0 if I plug 2 in. Can I divide by 0? No, das ist verboten. Okay, so that's the problem. Okay, now that said, what we can ask is, what is the limit as x approaches 2 of this thing? Okay, separate question with a potentially separate answer, but we can't just plug 2 in and call it good. Okay, if we could, this would be too easy and we wouldn't be discussing it. Okay, all right, so what we're going to do is we'll use Mathematica here, which is kind of like Desmos, only it's way more powerful than Desmos. Okay, and let me blow this up so it's easier for you guys to see. So let me do this. Let me put this on the right-hand half and this on the left-hand half. Isn't that magic? Yeah. Okay. So a couple things we want to do. First off, let's just define the function. And okay, there, right? And this is just how you define functions in Mathematica. Don't worry about the syntax and the underscore and stuff. We'll talk about all of that later. But for now, I'll just drive. Okay, and then I'm going to plot this thing. Now we're interested in what's going on near x equals 2. So let me graph it, say, from 0 to 4. Okay, just to start. And we'll see what we get. Okay, good. All right, so just looking at the graph, what do you think the y values are approaching as the x values approach 2? 0 seem reasonable? Okay, and that is in fact what it is, which we won't be able to necessarily prove today, but we can at least get some strong evidence for it. Okay. Okay. So here I graphed on the interval from 0 to 4. Right. What was the whole point of the warm up? Is that, well, what happens if I start to zoom in so that I'm looking at a small range of x's that are around, in this case, 2. Okay, the problem point. Okay, make sense? All right, so what should I maybe do this time for my viewing, the x range of my window? What makes sense to try next? All right, 1.5, 2.5, because that's on the sheet. Yeah, that's fine. So we're zooming in a little bit. Okay. 0 still seem plausible. Okay. All right, so let's zoom in even more. And if we were to do sort of like you guys did yesterday, right, then we'd probably do something like 1.9, 2.1, right? Okay. And all right, here it starts to look a little bit funky because, well, first off, do you still think 0 is the correct answer? Okay. But why is it sort of starting to get funky? Well, look at the range on the y-axis there. What kind of numbers are we looking at? Yeah, like tiny doesn't even begin to describe it, right? Things with 10 to the minus 44, right? You know, if we were talking about that many meters, we're talking about like, you know, grains of salt compared to a boulder where the boulder is a proton, right? So really, 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 really tiny. And you'll kind of notice that the graph well, maybe it's a little hard to see on the screen. You see how it kind of looks like, little sticks, right? Where what's essentially happening here is that's not actually what the graph looks like, right? It's nice and smooth, but we're at such a small precision that the computer can't be precise enough to graph this. And so that's why it kind of looks a little bit janky, okay? Just because of the extremely small numbers that we're dealing with. But does it kind of make sense? Yeah. Okay, so are we still convinced that 0 seems to be the answer here? Okay, now that's from the graphical point of view. All right, but the other thing that you guys did yesterday was what? Yeah, you made a table of values. Okay, you plugged a bunch of stuff in and you saw what you got, right? And you looked at those table of values and you say, yeah, that looks kind of like the graph and it looks like it's approaching whatever the number was. Okay, so it seems plausible, right? So let's do the same thing to make this table here with our uh, values. Okay, now, how did you guys actually do the arithmetic yesterday? You had a function, you had some numbers you wanted to plug into it. What did you do? Yeah. Okay, plugged it into a calculator. All right, and that's essentially what I'm going to do here, but I'm going to be a little bit clever. By having defined the function as f in this case, all I have to do is, for example, this. Oops. If I do f of 2.5, it's going to spit out the answer as 0.0625, right? So I don't have to actually manually do the arithmetic or, you know, plug 2.5 in, subtract 2, square it, then divide, then put a negative in front, and then do 2 to that thing, right? That would be a lot of steps here if I did it one at a time. Well, I don't have to do that because I can make the machine do it. All right, so let's just calculate all the rest of these things. And the way I'll do that is just type all of them in. Oops. 2.01, 2.001. Okay, and then now we'll come from the other side. Okay, so the square brackets in Mathematica function sort of like parentheses, so f of that thing. You always use square brackets in this program. That at first is annoying, but then you realize it actually is nice. Okay, so what do we get? 0.0625 for the first one. When we plug in 2.1, we get something times 10 to the minus 31st. And then what do we get for 2.01? Yeah, 0 point and an error, okay? That this number is too small to represent as a normalized machine number. Precision may be lost, okay? So is it 0? No. Okay, when I said it, let me qualify what I mean. Is this number f of 2.01 equal to 0? No. Is it really damn close to 0? Yes. Okay. And f of 2.001 is that a positive number? Okay. It's just really, 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 really tiny. Okay. All right. So do you still think that the limit is 0? Yeah. Okay. Seems reasonable, right? All right. So this example, okay, is meant to serve as a bit of a contrast to the exercise that you guys did yesterday, right? Yesterday, everything worked out great. It was all made total sense. It was pretty obvious that the limit was whatever number it was, right? Here, at least from the big picture, like plugging in 2.5 and graphing it, Like, were you pretty convinced that this limit was 0 as we approach 2? Okay, but it's not quite as clean cut as it was with the other example, is it? Okay, and so what this illustrates is that there's a bit of a limit, if you'll pardon the pun, to working with numerical data and graphs in terms of thinking about limits. Okay, they're fine as a, why is this happening? Okay, why did that happen? Hang on. Let me unplug this for now. Okay, I'm not sure why that happened. Okay, dang it, come on, computer. I don't have time for you to be janky this morning. Okay, stay. Good computer. Okay, so anyway, so if there's sort of limits to doing things numerically and doing things graphically, well, then what other tools are we going to have at our disposal? Right now, we don't have any, okay? So what we're going to have to do is sort of build up an algebraic way of dealing with these things that allows us to not necessarily have to rely on graphs and numerical data, okay? Because sometimes they can, well, lie to us is not really the quite the way I mean it, but they're not foolproof. Okay. All right. So let's now look at this graph here. Okay. And let me sort of zoom in on it. Okay. So we've got a graph, right? And what we want to ask is, what are the following limits? Okay. So first off, what does this symbol mean, right? Limit x arrow 1 f of x. Okay, what is this? This is asking a question. What question is it asking? Yeah. Uh-huh. Equals something, right? Okay. So what it's asking is, as x approaches 1, from either, really kind of both sides, what are the y values approaching, if anything? Okay. If the y values seem like they're approaching a specific number, then we say that the limit is that number. If they don't seem like they're approaching a specific number, then we say that the limit doesn't exist. Okay. So looking at our graph here, what are sort of the points that we might be interested in where something kind of funky might be going on? Well, definitely at 1, because there's this hole. Definitely at 3.5, because there's a hole and a dot. Okay, and 2 and 3, well, we'll see what's happening there. Okay, so let's start with 1. So as my x values get close to 1, what are the y values getting close to? 1, and it happens to be the same number here. Okay, that's coincidence. And maybe just looking at the graph, it's maybe slightly smaller than 1 because the dot, or the hole looks just a little bit under. So let's just say it's 0.9 just for sake of demonstration. Okay. And if all we have is a graph of some random squiggle, is that enough to really nail down the number? Can we at least ballpark it? Yeah, okay. So let's say it's just 0.9 just for, like I said, sake of discussion. Okay. So would we agree based on the graph that the limit as x approaches 1 of the function is 0.9? Seem reasonable? Okay. Now here's where we have to be careful. Can I plug 1 into this function? Okay. So I'm not asking what the limit is. I'm asking what's f of 1. It's undefined. How do you know it's undefined just based on the graph? Because there's a hole there. Okay. Does that make sense? All right. Now, let's contrast this. Where else do we see a hole? 3.5 on X, okay? So what is F of 3.5? 2. How did you know that? Yeah, because there's a dot, okay? So the hole is at Y value, what, like, looks like about -1, right? And if there weren't that dot up there at 2, what would F of 3.5 be? Undefined, okay? But because there is a dot, it is defined, and it's defined to have the value 2, which is the Y value of the dot. Okay, so are we clear on that? Now, that's a separate question to what is the limit? Okay, so as the X values approach 3.5, right, so if we were to do this kind of like we did with the last problem, and I had the function, what I'd be asking is, what's the Y value at, say, 3.3 and 3.4 and 3.6? What do those values look like they roughly are? They're pretty close to -1, right? Okay, so would we accept that the limit here is probably like -1-ish? Okay, so cool on that. We uno. Okay, and just so we're all on the same page, what does we mean? What does no mean? What does u mean? Huh? What does u mean? No. Or. So we uno means yes or no. Okay. Actually, though, you do have to be a little careful because there's oo and there's oo. And one of them means where, and the other means or. Right? Isn't that fun? Yeah. So anyway, okay. So now, what about at 2 and 3? What do you think those two limits are? At 2, what do we kind of think is going on? Maybe -1.5, roughly? Seem reasonable? Okay. All right, what about at 3? Kind of right there. So what does that look like? 1, roughly? Okay. So what are all 4 of the limits in order? What did we say that the first one was? Like 0.9 or something. It's just a little bit underneath 1. Okay. And then this one was -1.5, roughly. And this one was 1, roughly. And this one was, yeah, this -1, roughly, kind of where that hole is. Okay, so we got that, right? What about the values of the function, right? So we just figured out 4 limits. What is f of 1, f of 2, f of 3, and f of 3.5? Okay, so what was f of 1? Undefined. What was f of 2? The same value. What was f of 3? The same value. And what was f of 3.5? 2. Okay, so what's the moral of the story here? Not necessarily, right? It's not guaranteed that the limit's value and the function's value are the same thing. Sometimes they are. Sometimes they're not. We've got 2 examples of each. Okay. Sometimes they're not equal because the function is not even defined. We've got an example of that. And another time they're both defined but different numbers. Okay. So what this means is we can't just take limits by plugging values into functions. They literally are different questions. Okay, now sometimes by coincidence they have the same answer, but not necessarily all the time. Okay. Now, looking at that graph, could you suss out maybe what's the condition under which they are in fact the same value? Because we had 4 examples here, 2 where it worked and 2 where it didn't, yeah. Where there's not a hole, okay, and there's a lot of ways that we could sort of express the idea of there not being a hole. So what kind of other technical mathy words might you use here? Ah, bingo. Okay, these two things are the same when the function is continuous. In fact, it's the definition of continuity, and we'll see that later. Okay, now, what does continuous mean? What was the high school definition of continuous? Yeah, the pick up the pencil business, right? You can draw the graph without picking up your pencil off the piece of paper. Okay, was the high school definition of continuity. And that's not a really horrible definition, okay? It's certainly an intuitive definition, okay? We'll give it the precision it needs here in a few days, okay? But it's essentially going to come down to this limit issue, okay? All right, so does that kind of make sense? Yeah? All right, so let's carry on then. Okay, so let me blow the text up, okay, and let's do here. Okay, so like I said a few minutes ago, what we've seen is that it's not enough for us to just work with number crunching and graphs, okay? And so what we need to do is develop sort of an algebra of how to work with these things, okay? And how to put them together if we've got a complicated function, how we can sort of break it apart and examine the pieces separately and then build up the answer. Okay, now let's talk about the first two of these identities, okay? The first one, if I take the limit of a constant function, what do you think I'm going to get? That constant, okay? Last time I checked, that's the definition of the word constant, okay? Now, from a graphical standpoint, how might we establish this? So somebody give me a constant function. Give me a constant. 3. How creative. Now, I don't really need to do this, but before I do it, what am I going to see when I hit enter here? I should expect to see a horizontal straight line, right? Okay, so graphically, if I pick any x value, it doesn't matter in this case, what are the y values close to that? 3. They're 3 everywhere. It's a constant function, okay? And so what is the limit of a constant function as you approach some number c? It's just that constant. Okay, does that make sense? Okay, so the first two, like I said, are easy. Now the second one, what would change if I were to graph this one? What function am I dealing with? Okay, well, so what's the thing I'm taking the limit of? X, so that's my function, right? Okay, so let's go back to the graph. Let me change this to X. Not surprisingly, what do we get here? Yeah, straight line. Okay. Now, one thing maybe to mention is, does that look like it has slope 1 just from my graph? Well, yes and no, right? Why yes? Does it, or maybe why no? Why does this not look like it's slope 1? Well, slope 1, you would expect to see a 45-degree angle here. Yeah, but this clearly looks like it's a little less than 45 degrees angle. Okay, but the slope is actually 1, and how do I know that? If I go over to 1, what's my y value? Right, so the rise over run is in fact 1. So what's happened here is that the axes aren't both on the same scale, and so it doesn't visually appear to have the correct slope, even though mathematically it does. Okay, so moral of the story, you have to have your axes to really know for certain. Yeah? Okay, but we've got the axes, so it's all good there. Okay, so pick an x value, any x value. And it doesn't even have to be on the graph as I've drawn it. I can always redraw it. 2. Okay, so let me expand the graph very slightly, just so that 2 is not at one of the edges. And uh, and I'm going to tweak the scaling factors here so that it actually looks like it's slope 1. Okay, just to make it be fancy pants. Okay, so graphically, as x approaches 2, what is y approaching? Pick another number. As x approaches 3, what's y approaching? We noticing a pattern here? Okay, so if we have a linear function, or just x in this case, right? As x approaches something, what does y approach? That same something, okay? If it's just x, which it is for this example. Okay, so does that make sense, right? So those two are pretty straightforward, right? And then the next 4 are, or the next, group of these things, right, is, well, how can I build a complicated function out of simple functions, right? What methods do I have to combine things? Like, what algebraically can I do? Well, I can add functions. I can subtract functions. I can multiply functions by either numbers or other functions. I can divide them. I can do exponents. I can do square root type things. And then we'll talk about number 9 later because that gets us a few extras. Okay. But all of the things from algebra that you're allowed to do with functions, right? Add, subtract, multiply, divide, square root, exponentiate, compose functions. So that'll get us things like taking logarithms or stuff along those lines. Okay. But I can do all of those things to put simple things together to make more complicated things, right? And so, in the same way that, like, let's say I give you some really nasty function that's got some, gigantic, it takes, an entire chalkboard to write down the formula, and I give you a number and I ask you to plug that number into it. Okay. Would you all eventually get the right answer? If I gave you as much time as you needed and as much paper as you needed and maybe some coffee and right, would you all eventually get the same answer? Okay, why would you eventually get the same answer? Okay, other than the fact that you guys are a bunch of, you know, smart, well-educated, uh, Wabash gentlemen, right? If I did this with students at the alleged university to the south, what would happen there? It'd be a train wreck, right? No, not really. Whatever. Okay, so why is it you'd all get the same answer for some complicated formula? Well, do we have an order of operations that we've agreed on? Yeah. So when you guys plug things in, you're looking at some horrible formula and you're dissecting it and saying, okay, the order of operations says I need to do this first, then this, then this, then this, and then eventually you finish, right? And you guys have been conditioned over however many years of schooling to obey that order of operations, right? And at this point in your life, do you really have to think about the order of operations? No, it's automatic. You just do it, okay? When you first learned it in, I don't know, when did you guys learn the order of operations anyway? When did Aunt Sally come to math class? Third or fourth grade? Yeah, okay. Something like that. Does that seem reasonable? I mean, maybe they didn't mention exponents yet, but parentheses and multiplication and division and stuff, I would hope you were doing by third grade. Yeah? Okay. So it's just as natural to you guys as having memorized your multiplication tables, which please tell me they still make you do that in school. Uh, yeah. Because, of course, when I was in school, you guys are maybe starting to get a little bit young, but um, what was it that the teachers always told us in school? You're not going to be walking around with a calculator everywhere you go in your life. And then, yes, we are. So, um, yeah. Okay. So, anyway, that same sort of order of operations is what we're going to be using algebraically to break up big, complicated, nasty limits into constituent pieces. And here are all the rules for how we put them together. Okay. Now, let's take, for example, the number 3 here, the sums or the differences. Okay. So I need to have an assumption here. I have two functions, f and g. And they could be whatever functions, who knows. And I'm approaching x equals c for both of them. Okay. And let's further suppose that if I just looked at function f, that limit is the number L. And if I just looked at function g, that limit is the number m, okay, whatever those numbers are, okay? So given that, like, any questions on the assumption here? So that's the part at the very tippy top of the screen, okay, that we've got two functions and their individual limits are L and M respectively. Gucci? So what do you think would happen if I added the two functions f and g together and then took the limit? L plus m. Wouldn't that make sense to just get the sum of the two limits? Yeah. Okay. Now, why does that make sense? Okay. Keep going. What other reasons? What other demonstrations could you give, men? Yeah. Okay. So that's getting, like, think about it from a graphical perspective. What does it mean to add two functions graphically? What do you do to compute their y values at any given point? The new one. You just add up the two y values of each function, right? So if I added these things graphically, right, the y values at every point are going to be the sum of the y values of the individual things, right? And so would we expect this to hold if when we start doing the limit questions? Does that seem reasonable? Yeah. Okay. Now, let me be clear that we're not actually proving this. Okay, there is a way to prove this, but it's a little technical. Anybody thinking of being a math major? Well, Eddie, you took analysis, didn't you? Oh, or in 333? Oh, okay, never mind. So anyway, there is a way to rigorously prove that this works, and but that would make you guys all cry, so I'll spare you, at least for now. Okay, so, right. Now, if it works for adding, should it work basically the same for subtracting? Right, because what's really the difference between addition and subtraction? It's not really a difference, right? They're kind of the same sort of type of operation. Okay, now, what about if I multiply by a constant? Okay, now I can think of this in a couple of ways. One would be like, let's say that constant is 7. Okay, so what I would be asking is, what's the limit as x approaches some number of 7 times f of x? Does 7 times the previous answer seem like a logical guess? Okay, and here's another way to think about it. What does 7 times a function mean? What's another way to think of 7 times something? Well, how about that thing added up to itself 7 times, right? Well, if I'm adding something to itself, can't I just then use the result previously, right? So same idea. Okay. So anyway, but that said, the scalar there, so I picked 7 for sake of demonstration. Does it have to be a whole number? No, of course not. Okay. Now, so let's say I made it 3.5. What does it mean to add something to itself 3.5 times? Well, okay, the analogy starts to break down a little bit here, but do we at least kind of get the idea? Yeah. Okay, good. So in the same way, like if I gave you two functions and I asked you to compute the product of the two functions at a given point, what would you do? You'd plug the number into each individual one, you'd get whatever answer you got, and then you'd multiply those answers. Okay? So would we expect that the same thing is going to work with limits? Yeah, seems reasonable. Okay? So the limit of the product is the product of the limits, assuming that both of the limits actually individually exist, right? That was the big assumption that we had up there at the top. Okay, so then we come to the fun one, division. Because what's the problem that we might run into with division? Yeah, what happens if the bottom limit is 0? Then we have problems, okay? And it might work out in certain examples, but it might not in others, okay? And we'll actually see a lot of examples of that issue, okay, where if we were to just start plugging in numbers, we would appear to have division by 0 problems, okay? All right, so we'll deal with that later. But as long as the one in the bottom's not 0, everything's cool. You just divide the answers, and that's the end of it. Okay, does that seem reasonable? Yeah, okay, good. What about if the one on the top is 0? Is that a problem? Assuming that the one on the bottom is not 0? Should that be a problem? Is 0 divided by something a problem? And what's the answer to 0 divided by something? 0, unless the bottom also happens to be 0. So what's 0 divided by 0? Huh? It's not 1. Okay. And we'll talk a lot about this. 0 divided by 0 is even worse than undefined. It's what we call indeterminate. Okay. Now, I can do one better. Pick a number. I can come up with a situation in which that situation, 0 over 0 equals 2. Somebody pick a different number. I can do the same thing with 6. Can do that too. Also can do that. In fact, if you give me any number A, I can write down a situation where 0 over 0 looks like the number A. Okay? Pi, doesn't matter. Okay? Okay, so this is what we mean when we say it's indeterminate, is that like it just depends on what situation you're dealing with. It could be any number, right? It could be anything. It could be a boat. PETA? No. You guys know that Family Guy? okay? When they win, it's like you can have the boat or you can have whatever's in the mystery box. And Peter wants the mystery box because there could be anything in there, including. You guys all know that what I'm talking. Well, then why aren't you laughing? This is hilarious. Okay. All right. Anyway, right. So, right, it could be any number, and we don't know necessarily which one it's going to be. Okay. Um, powers work fine, right? So the limit of a thing to an exponent is just the limit to that exponent, with a couple of caveats. Okay, because what kinds of exponents can we deal with? Like if I ask, what would be an example of an exponent? What might you say? Okay, to the fourth power. Great. Limit of something to the fourth is the limit to the fourth. Great. But what else could these exponents be? They could be fractions or they could be negatives. Okay? What do fractional exponents represent? Square roots, cube roots, those sorts of things. Okay? Which is the next situation. What do negative exponents represent? You put that thing in the denominator. Okay. So if we're putting things in the denominator, what might be a problem? The thing could end up being zero, and that if it is, we got an issue. Okay. So there's that little asterisk, right? And then the second issue we need to deal with is if we're dealing with roots. So for example, the square root, how could I write the square root of x other than just, the square root symbol in x? Yeah, if I wrote it as x to the 1/2, that's the same thing, just a different notation, correct? Okay, so what's potentially the issue with the square root? What am I not allowed to do to square roots? When do you get an imaginary number from a square root function? When the input is a negative number. Okay, so like if I did the square root of -1, am I allowed to do that? Not not in this class, I guess maybe is a better way to put it. So you guys, when you were in algebra and you learned about imaginary numbers, you said, okay, we'll call this square root of -1, whatever the heck that is. We'll call it I, and we can do stuff, right? But I is not a real number. It's an imaginary number. It's a different, object. Okay. We will only deal with real numbers in this class, okay? Because doing calculus with imaginary numbers, while possible and while really freaking cool, is also like 3 or 4 classes down the line. Okay. So if you really are like burning with desire to know how it works, you better become a math major to be inducted into the secret society of. I'm probably not doing a very good sales job here, am I? But okay. Anyway, so yes, but point being, when does that problem occur? Whenever we're trying to take a square root or a fourth root or a sixth root or basically an even root of something that's negative. What about the odd roots? So is the cube root of -1 a problem? Square root of -1 is definitely a problem. What about the cube root of -1? Okay, so what is the cube root of -1 asking? Find me a number so that when you multiply it by itself 3 times, you get -1. Can you think of such a number? How about -1? Right? -1 times -1 is 1, times -1 is -1. Okay, so odd powers don't have this problem. It's only the even ones that do. Okay, that makes sense? Yes. Right. Yeah, the positives, they're both cool, right? And also 0 for that matter, because what's the square root of 0? 0. Okay, so no issues there unless that happens also to be in the denominator, right? Yes, so yeah, good point, right? And so this is here that if n is even, we require that the function be positive. Okay, so, or sorry, not negative, because it could be 0. Okay, does that make sense? Okay, So, and then compositions we'll talk about here in just a second. Okay, so basically, the way composition works comes down to this, that if you know that the limit of the inside thing works, you just take that number and plug it into the outside thing. Okay, so let me maybe give a more concrete example here. Right, so let's take, for example, well, let's just take something like e to the x minus 7, okay? And let me do the limit as x approaches 9, whatever. I'm just making up a number here, okay? What do you think this is? Well, would it make sense that this is e to whatever the limit as x approaches 9 of x minus 7 is? Okay? Because if I asked you, like if I just gave you this function and I said plug in 12 to it, you'd do 12 minus 7, then you'd do e to that thing, right? And you'd get whatever. Okay, so should we expect that this property will hold with the limits as long as the thing in the x that I'm taking the limit of, the inside part, is okay? Seems reasonable. And it turns out that this is in fact true, provided that a couple of things. So in this example, what do I get? What's limit as x goes to 9 of x minus 7? What number do you guys think? 2. How do we get that? Well, what's the limit of x minus 9 of x? Right? What's the limit as x approaches 9 of 7? 7, it's a constant. And we have a difference, so the difference rule applied. Right? And last time I checked, what's 9 minus 7? Okay? And so here I would get e to the second, whatever that number that is. Right? Okay, so does that kind of make sense? All right, so function composition is going to work mostly fine. Okay, all right, so what I'd like you guys to do is, and we'll continue this with on Friday, is take a look at the ones here that on this last page that we didn't quite get to, okay, where we have some specific examples and some specific numbers. All right, try all of those, and that's what we'll start with on Friday. Okay, now, and I'll go ahead and quit the stream, and see you later.